talk much about that an s orbital. An s orbital is a spherical orbital. You can kind of see it there. I'll just do a drawing of it real quick here. And so this is an s orbital. That's where the electrons are going to be hanging out. And then a p orbital is just a little bit, kind of a dumbbell shape. That's not a very good drawing of it. And I'm not going to try to draw some of these because I just don't have control over this pen to where it works very good. But it's kind of a dumbbell shape is what it is. Okay, and so that's like a p orbital. And then, so what happens, we'll have a bond that'll happen. Okay, and so we've got carbon. And carbon is 2s2, 2p2. Okay, it has the 1s2, but it's an inner level, and so these are the only electrons that are going to be involved in bonding. And so we do our orbital notation down below, and we see that there's carbon. But we know carbon bonds can have 4 covalent bonds. So when we wrote out CH4, we knew that it bonded this way. And each of these bonds are equal energy, equal length. Everything about them are the same. And then you go, well, how does that work? And so what will happen is we'll get a combination of what's called an sp3 orbital. That's not an s, not a p, but a combination of the two when it bonds. And it's hard for me to look at these to make sense of them. I just don't think it's a very good model that when we draw these out, it's hard to visualize how it happens. But here's the 2s2, and then here's the 2p2. And basically what we're saying is we're going to create an equal energy bond that has a combination of an s and p. It's kind of like, for example, a car can run off of electricity or gas, called a hybrid. So it can run off of both.
So since there's 4 lines, is it combining the 3 and the 1, and in the arrows there's 4 different ones? So it's just...
Yeah, it's combining the 2s and the 2p. And originally there's 4 arrows, and so what it's doing, it's saying we're going to take the ground states of those orbitals, and we're going to create what's called a hybrid orbital. And what's a hybrid orbital look like? Again, models just are hard to kind of make sense of. And if you look on page 356, they show you a hybridization of an S and a P. Take it for what it's worth. I mean, just take it for what it's worth. That's kind of what they symbolize it for. And again, models aren't really good, I don't think, of showing this because they can get real kind of tough to see what's going on. Okay? I'll give you some information about sp3 hybrids. How do you know if a particular atom within a Lewis structure would be considered an sp3 hybrid? How would you know? You don't want to go back and forth to do it. So, what sp3 hybrids have? You know, what's some characteristics of it? Okay, they have 109.5 degree bond angle. So they'll always have 109.5 degree bond angle. Okay. So when we look at a tetrahedral structure, that's what we're going to take a look at. So that's another thing we can look at, is we can look at the electron pair arrangement is a tetrahedral. So anything that has a tetrahedral shape with its electrons, whether they're shared or unshared pairs. We also have this thing called effective pairs, and I'll explain what an effective pair is. But it has 4 effective pairs. An effective pair would just be how many links are presented to a particular atom. So if we look at this atom in the center, it has 1, 2, 3, 4. It has 4 bonds there to the central atom. So they'll call them effective pairs. Okay, another one would be, that's a sp3 hybrid would be, this would be an example of it. So if it's an unshared pair, it's an effective pair. So this has 1, 2, 3, 4 effective pairs. So that would be nitrogen. Around nitrogen, nitrogen is an sp3 hybrid. Questions?
So what
You might want to read some of this. Go ahead.
Is there such thing as an ineffective pair?
No, there's not.
Okay.
And so you just count how many. Now, if it's a double bond, that counts as just one effective pair or one link. So you look to see how many unshared pairs or how many links that you have, and that's an effective pair. So that would be a tetrahedral shape. That would be an sp3 hybrid. How it works. Okay, the last thing I'll show you. I didn't want to draw this out because I'm terrible at drawing this. I'm going to show you where these sp. So if you look at these orbitals, this is an orbital here, and this is an sp3 orbital. Just that blue part. Okay, so that's an orbital that is a combination of a p, 3 p's and an s, or a p and an s. This is an sp3. This is an sp3. And this is an sp3. So what that's saying is that that electron in that location takes on the characteristic of a combination of an S and a P, and they call it an sp3 hybrid. Okay? That's all it's saying. It's saying it's in this form. This is the sp3. And that's what they show was the orbital, what it looks like. And if you notice, it's going to be 109 degrees and a half between the bonded angles around carbon. So each of these bonded angles is 109.5 degrees. And that gives you that tetrahedral shape. I don't want to put Celsius, but just degrees. Okay, this electron for hydrogen is the 1s. So it's not a hybrid. Does that make sense? The hydrogen is not a hybrid. What its orbital is, it's a sphere orbital, right? Okay? Later on, we're going to talk about this bond right here and what it is. Okay, and I'm going to give you a little information about it now, and we'll talk about it later. This is called a sigma bond. So we're going to get into sigma and pi bonds, and that's a sigma bond. How can you tell a sigma bond? A sigma bond is when your two lobes face each other. Sigma bond is when the two lobes are facing each other. I guess they're perpendicular to one another. They're kind of facing one another. And so this bond we're going to call a sigma bond when we see it. So anytime we see two lobes facing one another, interconnecting with one another, that's called a sigma bond. Any questions you have? So in this case, I have 1, 2, 3, 4 sigma bonds. 1, 2, 3, 4 sigma bonds. Okay? Any questions about an sp3 hybrid? Thank you. Okay, it's called sp3 hybridization. It's when they take an S and P and they again, this is theory. This is called the localized electron pair theory. And it's just talked about in section 9.1, and that's all the farther we're going to go with it. Okay. So then, there's other hybrids. Okay? There's an sp2 hybrid. Okay? So what's a has? So what are some characteristics of sp2 hybrids? Well, the bond angle is 120 degrees. Okay, that's what it is. So any bond angle that you have, it has 3 effective pairs. We'll give you an example of that here in a second. Its shape the shape of the electron pairs. Arrangement is trigonal planar. And so all this goes with our shapes that we did and looking at them. But if we have a shape of a trigonal planar and we know that, then we know that that's, we memorize it, we know that's an sp2 hybrid. We know the bond angle is 120 degrees. We know we have 3 effective pairs. Okay. So here's an example of that. We just want to look at one of the carbons. One carbon or the other. So the bond angle here is 120 degrees. Between all of them, around the carbons. Okay, an sp2 hybrid kind of looks like this. I'm going to go ahead and show you it. We have the 2p, we have the 2s down here, got the line, it's just got the 3 lines, and then so what it does, it creates 3 of these energy levels here. That's an sp2. So this would be sp2 down here. And then we have one of these that still would be the 2p. I'm not going to get too involved in you knowing that, but what happens is an S and 2 of these P's hybrid together. And then you're left with this P, nothing happening to it. Okay? Nothing's going to happen to that. Okay? And that's going to be our pi bond. So we talked about sigma bonds and pi bonds and what they are, and we're going to talk a little bit about those here in a second. So, getting a lot of information today. Would encourage you to do some reading, just in that one section 9.1 to kind of help you with it a little bit. It's not easy reading. Questions you have about sp2 hybrid. Here in a second, I'm going to give you guys a different look kind of a drawing of it. Now you guys don't have to draw this diagram out because I'm terrible at drawing these out. And it's 3-dimension, which makes it tough. It's better if you could take a 3-dimension view of it. And I wish I had some 3-dimensional views of models that I could look at. I think maybe in the past we had some styrofoam ones we looked at. But we're not spending a lot of time on this either, so it's not like it's major concept, like stoichiometry or something like that. So, I'm going to cross through. Now don't draw this right now, and you may not want to even draw it, okay? All right? This is not the one I want, so that doesn't help with things either. Okay, this is the one I want. Okay. So if you notice, these two lobes are facing one another, so what kind of bond is this?
A sigma bond.
Sigma bond.
Oh, yeah.
And these two are facing one another, so that's a sigma. That's a sigma. 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 Okay, what they don't show you here, I'm going to draw in. Okay? So this is the 1s. This is the 1s. 1s. And then this is also 1s. This lobe is a combination of an sp2. So this is an sp2. This is an sp2. And this is an sp2. Same on this side. sp2. 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 Okay? Now what they're not showing you is another lobe. Okay? So this isn't complete because I'm going to show you this other lobe to help things out. So we have the sp2 covered. Okay, so let's look back at this. We have showed, with our lobes, we've showed these three. Okay? So we showed those three. 1, 2, 3. But what we haven't shown is that P
Oh my God.
there.
Extra 2p.
Okay, so, I mean, we can't leave it out. And so, where I got this from, they had two different drawings, and I want to put it all in one drawing. Okay? So what I'm going to do is I'm going to erase so it's not so much information going at you on this. And I'm going to show another lobe. I'll do it in a different color. Okay? And I'm gonna do this lobe, and this lobe will be right here. It's supposed to be a different color to identify it a little bit better. Okay, so this lobe is going to be here and here. And I'll have you look at a picture in the book that you can see, you can tell a lot more for. So this is 3 dimensions, so it's tough in a 2-dimensional drawing to show. Now the pi bond, so this is the sigma bond here. The pi bond is going to be the other part of the double bond. And this is the pi bond here. They're connected here.
So why are there
So it's connected here. That's one of the bonds. And the other bond, there's an attraction between these two lobes, and this is the 2p. Okay, that's the 2p orbital right there. These here are the 2p orbital. See how it's dumbbell shaped? That's the same orbital. This 2p is the same orbital. So it's like a dumbbell shape. It's going through the sea. And you'll never have to draw these, and I can't even draw them, even with them. So they're connected there. So here's one of the bonds, that's a sigma, and then this is the pi bond.
This is like mix pen. I think these machines are just breaking because mix is doing the same thing.
Yeah, well, I think it has to do with the reader, if I'm too close or not close enough, when it spreads out. Now, this shows better in the book. You look at bottom of page 359. It shows those extra 2p lobes. Make sense? There's the 2p lobes. And that's the pi bond. So, on this, a double bond, you're going to have a sigma and a pi bond. The sigma, the lobes face each other, they interface, and the pi bonds will also interface, but they're parallel to one another. Okay, and then, so that is the SP2. Questions? SP2. The last one is an SP orbital. This is the last one we're going to talk about. And if you turn over to page 360, it's going to talk about an SP orbital. Okay, and probably want to look on page 361 because that's going to show it the best. Page 361. Okay, and 361 will kind of look like this. Okay, there's a triple bond. So what this structure is here is C, triple bond C, bond H, bond H. So you guys could probably tell me the bond angle between the bonds there, right?
180.
180. So an SP hybrid is going to have 180 degrees in between the two bond angles on that particular atom. Okay, and if you look, these green ones up here, they are your pi bonds. And you have two sets of them. So when you look at this, you have a pi bond here, there, and there, and then you have the pi bond. So a triple bond will have two pi bonds and a sigma bond. Okay, so I'm going to go ahead and share the last little bit of information with you, and then I'm going to do an exercise that you guys are going to do tomorrow. I won't be here tomorrow, but I'm going to go through this exercise that will make it easier in which to decide pi bonds, bond angles, all that good stuff here in a second. Okay, if this thing will work for me, I might have to reset it to where it'll work better.
It's just not reading your pen at all.
Yeah, don't know. Maybe I'm out of batteries. Maybe I didn't charge it. Maybe it's been uncharged. Could be that too. Because I've had it out of the charger. So that could be it. Okay, so I got one more bit of information to give you, and that's an SP hybrid, some of its characteristics. How many effective pairs do you think?
2.
2 effective pairs. Bond angle, 180. Okay, and then it's going to be, shape is going to be, I think, linear. Okay? So, we're going to do this exercise, and you don't have to copy this down, but just kind of, we're going to fill this out. And so, this is a organic, like if you take organic chemistry, you'll be dealing with a lot of structures kind of similar to this. You should understand a little bit about them. Everything up here has to have 8 electrons around it. Okay, so we can go to each one, and we may have to add some dots. So this is a single. This has 1, 2 pairs. So how many more does this need?
2 more.
2 more. I'm going to put 1 here and 1 here. Okay. Carbon, does it need any unshared pairs?
It's got 4.
It's got 4. It's good. This carbon has this third. So if somebody's listening to this, we'll just underline it. This one is okay. Here. This carbon's okay. I think all your carbons are going to be good. How about this nitrogen?
It needs 1.
Needs 1 pair. How about this nitrogen in the middle?
It's Gucci.
It's good. How about the nitrogen at the end?
It needs 2.
It needs 2. And some of you say, well, doesn't nitrogen have to obey the octet rule? Not the case on this one. Do you guys see oxygen? This one needs 2. So that you're going to be asked to count and do some of this as well. So this one needs 2. That nitrogen needs 2. That carbon is good, good. This carbon is kind of like they put it out CH3, but we know a CH3 is C and then bonds around. So that's called the methyl group. When you get into organic chemistry, this is CH3's methyl. Okay, that carbon's good. I think everything else, oh, this nitrogen needs 2.
Oh.
I think we're good. Okay. So what I'm gonna do, let's find all the sigma bonds.
Ooh.
There's a lot of them.
Ooh.
Okay, and I'm just gonna number them in red so we can keep track. So this is 1. 1. This is 1. Oh, I gotta number them so I keep track of them. Duh. So let's go. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Is one of these a sigma? What do you think? What's the bond angle? How many effective pairs does that one have?
2.
Has 3. Doesn't it have 3? This is 1. I'll have to erase this. This is 1. This is 2. That's 3, right?
Yeah.
Okay. So, I'll get rid of these here. So that one's 3. And so, bond angle for that should be 120. And since anytime we have a double bond, one of those bonds is going to be a sigma bond. Does that make sense? Okay. So it's 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. There's actually 3 in here.
26, 27.
Okay, so we'll say 25 through 27, 28, 29, you're thinking this is stupid.
What about the one between the 2 C's?
30, 31,
And then there's one between the 2 C's.
here,
No, up one. Up and to the left.
here,
Now to the right.
Yeah.
Right there.
I didn't count this one either, right? Did I?
Yeah, no.
No, you didn't. You
Okay,
didn't do that.
so 32, 33. See what I got missing?
That was crazy. That's what I was counting.
Do I have every line have something? We good? Okay. So there's 33 sigma. So you say, well, 33 sigma bonds. Now this is an extreme. The ones you're going to do are going to be less than this.
No organic chemistry.
Yeah, you're going to be less than this. So the pi bonds are going to be easier to do. So anything that has a double bond has a pi bond, at least a pi bond. So
So we got the nitrogens at the bottom.
yeah, so we got 1, 2, 3, 4, 5. Is that it?
I believe so.
Okay, so we got 5 pi bonds. Okay, and so we don't have a triple bond. If we did have a triple bond, then we'd have to count 2 pi bonds with it. 1 sigma and 2 pi. Then the last thing you'll be asked to do, there'll be letters like that you'll have to do. And so like one will be, get this in yet a different color. So let's say that we have A. No, it doesn't show up very good. But then we have B. And then we have like C. And then we have D. And then, so then it'll ask you, well, what's the bond angle at A?
Which one's A?
This is
Probably
A.
number
Okay.
10.
Yeah, I can't read.
That's A.
Okay.
So what's the bond angle?
109.5.
109.5 is tetrahedral shape. We know they have, so tetrahedral shape. B.
Is that the 22 and 23 one?
Yep, that's the between 22 and 23.
120.
120. Because it's an SP what?
2.
SP2 hybrid.
Yeah, it is.
Okay, where A is an SP3 hybrid around carbon.
Right.
So that would be 120. How about C?
That's so linear.
What?
It appears.
Nope.
But it's got
Bends.
4 effective pairs.
4 effective pairs.
So, 109.5.
109.5. And what kind of a hybrid is it?
It's a SP3.
SP3.
Yes.
And then D, last one.
Oh.
So is that linear?
That's linear, yes.
That's linear, and what kind of hybrid is that?
That means
SP.
that it's an SP.
SP. Okay?
108.
So, that's a lot of information intake, and if we do something with it, it'll be something where you'll just go through like a molecule, and you get some practice tomorrow, like this, and then you just say what kind of hybrid it is, what kind of bond angle it is, if it's a pi or sigma. Remember, the pi and sigma differ in that you have your p lobe still there, and they're sharing on this p lobe right here, and that would be a pi bond. Okay, and then you have another pi bond here because they have their original lobes, and then right here is where you have your sigma. That's where your sigma is, and that's where you got a triple bond, and 2 of them are pi's and 1 sigma. Okay. All right. So I'll give you guys an assignment tomorrow.